We built a mixer zkApp in this builder program. We called it mCash. I will just quickly go over the team. This is us, and Murat is also in our team, but he didn't actively participate in this program. Murat and also Tuğçe and Hunter helps us our production products rather than this Mina's builder program. So what is a mixer? Mixer allows you to transfer funds from one account to another account without tracebacks. So you can use mixers to anonymously transfer your funds between your accounts. For example, Vitalik uses Tornado Cash mixer on Ethereum because all of the ETH on his account sits with the ENS named account. So he needs to transfer this ETH to another account to buy or sell something. So this is one use case. For example, prevent JAXs from watching your accounts is another case. And for example, you can pay for some service anonymously via off-chain key exchange. Also, this can be built on Mina Protocol. This is the general architecture of our zkApp. I will go over the code later, but let me just quickly go over this diagram. For example, this is our starting address. I think you can see my cursor. First of all, we call the deposit function via our web UI, and it calls the smart contract with two randomly generated fields. This is one of them is secret and one of them is nullifier. We hash them and get a commitment. So we insert a commitment to a Merkle tree, and this creates a commitment witness in our smart contract. And we check witness and update our route in the smart contract. And then later we can shift to another account. For example, some time has passed, and now we can supply our secret and nullifier to the smart contract, and it can check whether this secret and nullifier's hash, commitment is in the tree. If it is in the tree, it will give the deposited money back, and it will also add the nullifier to the nullifier tree. And we need to do this because we need to also prevent double spending errors in our smart contract. So while doing all of them, this operation cannot be traced back because commitment has never been revealed in both of the operations. And also it cannot be double spended as we inserted our nullifier into a Merkle tree. Let's go over. So what Snarky.js did provide to us? Previously, we worked on the mixers, especially on Tornado Cash. And Snarky.js significantly reduced the need of knowledge of cryptography. For example, if you need to build a mixer for Ethereum, you need to write circuits in different languages, like zkApp. And writing circuits is harder than writing TypeScript, of course. And there is a lot of options to do it, but it is still harder than TypeScript and Snarky.js. Also, you need a verifier contract to deploy on blockchain, and this also needs to another operation like maybe making a trusted setup ceremony, etc. So the all verification needs to have on Ethereum, and verification of snarks on Ethereum is not very cheap. And thanks to Mina blockchain, there is no need to build separate applications for proof generation and verification. We can generate our deposit proof, and we can verify them in one Snarky.js application in our smart contract. And all of the inputs are private by default, as we desired. While also withdrawing the proof of verification also generated by Snarky.js, and it is also accepted by the blockchain. Next steps, we are developing proof of innocence, an open source zk tool to prove non-membership of some group while withdrawing from Tornado Cash. For example, you can prove that you are not one of the OFAC sanctioned address without disclosing your entry address. Now we are writing the circuits for that. It will work on Ethereum, but we will also implement the proof of innocence to the mCash, this zkApp. Thanks to proof of innocence, mCash will have built-in but optional compliance-oriented feature. And this way, the mixer will also allow everyone, but you can exclude yourself from, for example, sanctioned address or hacker addresses. And I think this is good in terms of compliance. We will also work on a better UI and better off-chain storage solution. For now, we are just using an API and it sends requests through our front end, but it needs to be in the protocol. And we are waiting the final solution for the off-chain storage from the Mina side. And of course, project is open source, and we want to have a community-owned mixer because it is important to have an open source mixer in terms of trust needs. And if you're interested, please open a PR, raise an issue, or if you want to add something, please ping us. Thank you for listening. Now I will just quickly go over our front end and code. I will not make any transactions because it will take time, but we didn't have implemented the Aura wallet yet. It uses a locally stored private key. If I click the deposit, it will create 2 random fields, and I need to store them in my computer or in the paper. And after depositing, the current root will change, and I can change my also address, and I can withdraw using the same nullifier and secret. And if I try one more time to withdraw, it won't let me do it because I inserted my nullifier into a nullifier tree. This is the general structure of our repo. There is one UI, I won't go over it, but it is fully working right now. In the contract side, we have this mCash file. Like I said, we are storing the nullifier trees root, commitment trees root, and the last commitments index because we need to add all commitments next to each other. These are just for testing. There is 2 main functions in this zkApp. Deposit functions does the commitment hash generation and also checks the witness is correct, and it also takes 1 Mina from the caller because, for example, this smart contract will take 1 Mina and another smart contract will be deployed to take 10 Mina. After depositing, it updates the root on the smart contract, and it also emits an event to trace for example, we can generate the off-chain storage from these events if events are reliable. And in the withdraw session, we also generate a commitment and we check the commitments. In this part, we are doing one different thing. We are used nullifiers as Merkle trees, but to be specific, it is a sparse Merkle tree implementation. In sparse Merkle tree, we can verify that this root is filled or not, and it is useful for us to prove that we are not on the list or we are on the list. It is easier to prove than in Merkle trees. So this is also does all the verification and updates the root, and also returns the Mina to the caller. And this can also take additional arguments to, for example, you can return your money to another address. It is also fine. There are some helper functions on this side. We have also tests that is fully running, and there is just some also other helper functions. So, for example, testing the initializations and the other tests. And that's all on my side.